All right, so we're going to take a look at this example again of methane, 4 kilograms, and it's burning inside of a room, and the room is 4 by 5 by 3 meters. So we want to be able to determine the equivalence ratio, find out if it's overventilated or underventilated, and then use that information to find out how much of a specific product of combustion is being produced. So we call those the species. So for this example, we'll look at carbon dioxide. And then once we know that, we want to really find out the mass fraction and then the volume fraction of that species. And then once we know that, that's the information that we can use as a parts per million or a percentage to find out what's the impact on an occupant. So we looked at previously to this, how to balance the equation to find the stoichiometric ratio for methane. But just to quickly review that, we've got the methane or the fuel, and then we have the air that we're going to use as part of the combustion. We're adding the heat, so we have the combustion process. And then after that, we end up with some carbon dioxide and water. So that's under any normal combustion process for a hydrocarbon. And then we have the leftover nitrogen. And these numbers are balanced. We went through that process previously. And we said the nitrogen is inert, so it doesn't take part in the process, but it's important to have it there because it does absorb the heat as part of the process, that the fire's burning slower than if it was just oxygen, because a lot of the heat that it's producing is warming up something that doesn't participate in the reaction. So understanding this and going through this process is going to be vital for fire protection, to really understand what's going on and making proper decisions on designs. So in order to figure out the equivalence ratio, first we have to do that stoichiometric ratio. And we said that that is the difference between, or the ratio between, how much does 1 mole of air, or the combination of oxygen and nitrogen, weigh, what's the mass, divided by the molar mass of 1 molecule of the fuel. And we do that calculation here, and we find out that the air that we use is going to be 275 grams for the amount of air that we need to burn 1 molecule of methane. And remember, this is specific to methane. Right? So these numbers will change based on the fuel that we're using. And for methane, 1 molecule is going to weigh 16 grams. Right? So we've got that, the mass of 1 molecule of fuel, 1 carbon in that, and the carbon is going to weigh 12, have a molar mass of 12 grams. Then we have, again, 1 molecule. We have 4 of the hydrogens, and they weigh 1 gram. So we add all that up, and we get the 16 for the fuel, and the air comes in at the top. And if we do that division, then we find out that the ratio, the stoichiometric ratio for air to fuel, is 17.16. So for every gram of fuel that we try to burn, we're going to need 17.16 grams of air to do that. Right? So that's kind of the ratio that we need to keep in mind. And again, this is specific to just methane. So we change the fuel, all these numbers are going to change. So now let's try and find out what the equivalence ratio is for the methane that's burning. Right? We said the equivalence ratio is taking that stoichiometric ratio and then multiplying it by the actual amount of fuel and air that we have in the room. So the stoichiometric ratio is the perfect amount of fuel, perfect amount of air, that after combustion, all of them are completely consumed. So we don't have any more fuel or air left over, just all of those products afterwards. But we know that's not going to be the condition that we have, So we're going to take that ratio and multiply it by what we do have. And in this case, what we do have is 4 kilograms of fuel, and then we have a room that's 4 by 5 by 3. Right? So in order to look at that, to get the air, we know the density of air. We're going to say it's 1.21 kilograms for every meter cubed of volume. And we know the dimensions of the room are 4 by 5 by 3. So if we multiply length times width times height, we'll get the volume of the room. And if we multiply the volume by the density, we'll get the mass of air. Right, so that's what we're doing here. And so we end up with 72 kilograms of air would be inside a room that's 4 by 5 by 3 meters. And we're given that the fuel is 4 kilograms. So we have 4 kilograms of methane, 72 kilograms of air. And the equivalence ratio then is just the mass of fuel divided by the mass of air. And then we multiply that by that stoichiometric ratio that we just looked at. Right? So we know we actually have 4 kilograms of fuel, and we're dividing it by the 72 kilograms of air that we actually have. So that's our actual ratio. And then we multiply that by the expected, what we would hope, stoichiometric ratio for perfect combustion. And we end up with 0.9511. Right? So we have a value that is less than 1. All right, so we know if we're looking at that the situation is going to be over ventilated. So we have less fuel than we would expect, or more air than we would expect. All right, so now that we know that, we want to take that value and then start using it to actually figure out what is being created. And so for this example, we'll take a look at the production of carbon dioxide. So we'll just skip over some of this stuff and we'll get right to that example. All right, so for the species, we are going to use those tables, but we've already looked at them. So we look up the value for how much, in this case, carbon dioxide is going to be produced for that specific fuel under the conditions of overventilated. So we did that equivalence ratio to determine, is it overventilated or underventilated? Do we have enough air or not? And in this case, we have enough air. So it's going to be a fuel-controlled fire. And so we can look that value up, and then we multiply it by the amount of fuel that we're actually burning, which was that 4 kilograms. And that will tell us how much of the carbon dioxide is actually being produced. All right, so let's take a look at that. Here. And we'll just circle over. We've got the methane, and we want to know how much carbon dioxide is produced when we burn methane. And so we're going to look for the carbon dioxide production, and we look for methane, and we have 2.72. And that is gram per gram. So that's 2.72 grams of carbon dioxide will be produced for every gram of fuel that we burn. So we're actually creating more carbon dioxide than the fuel that we're burning. And that sometimes is kind of hard to wrap our head around. But if we're burning methane, we have CH4, but we're adding to it some oxygen. Right? So the oxygen is getting added into the carbon of this molecule. When they break down and reform, we're ending up with CO2. So we're actually adding some mass into the production there. So we look up that value, 2.72, and then we're just multiplying it by the 4 kilograms of methane that we're going to burn. And that gives us 10.88 kilograms of carbon dioxide. So we should have 2.72 times the amount of fuel. And so that looks like that's about right. And so we're actually getting that extra bit of carbon dioxide produced there. So now we know how much of the species is produced. But that doesn't really tell me how dangerous the situation is. So I know that there's 10.88 kilograms, but it's also just as important to know where is it being produced. And that's how we determine the mass and volume concentration. Right? So knowing the mass of it is important, but what is that concentration? How much am I going to breathe in based on the geometry of the enclosure? So what's really important is being able to determine the parts per million. Right? So how many of the million molecules are going to be carbon dioxide? So when I breathe in, now I have a better understanding of how much carbon dioxide am I going to breathe in this example. It's carbon monoxide in another example. It's the same process, but we look up the different values there. Okay, so it's important to understand how to get these parts per million, and then we can look that up to find out what does that value mean for life safety. So in order to get the mass concentration, we're going to be looking at this equation down here, which tells us the mass concentration or the mass fraction is how much of the species do we have. So we just calculated that. That was our 10.88 kilograms. And we're going to divide that by the mass of air in the room. Okay. What we actually should do is this process over here. So the mass of smoke, so it should be mass of smoke rather than the mass of air. But we're going to look at this example and you'll see it's pretty much the same. It's a pretty accurate simplification just to calculate the mass of air in the room. Okay, but we take the mass of the carbon dioxide, divide it by the mass of air, that will give us the mass concentration. And then that's not the exact concentration we want. We actually want the volume concentration. So in order to get that, we're going to take the mass concentration and we're going to divide it by how much one molecule of the species weighs. So in this case, the mass of the species is carbon dioxide. So it's going to be a carbon plus 2 oxygens. So we'll do that calculation. And then we're multiplying by the 29 there. And that 29 is really just the molar mass of the air. Okay, so we know that there's 21% oxygen, 79% air, 79% nitrogen in the air. And then we know that nitrogen's 14 and there's 2 of them, oxygen 16 and there's 2 of them. And we do that math and we end up with the molar mass of 28.84. Okay, so that's what that 29 is. It's just the molar mass of air dividing by the molar mass of the species that we're concerned about. And then we multiply that, and that gives us our volume. How much space is the actual species taking up in that relationship with air in the room? And that gives us a better understanding of concentration. So this one, when we're looking at the X species, this is going to be the one that we use in our calculations. And so that, once we get that value, we're going to convert that into either a percentage or parts per million, depending on the equation, how we need it to be. We'll do that conversion. So this number will be a fraction or a decimal between 0 and 1. And then we multiply it by 100 to get a percentage, or we multiply it by a million to get the parts per million. So let's do that. So from the previous example, we're going to look at the actual method of what we should do. And so we have the mass of smoke. So we have to look up the mass of all the molecules that were produced, so the water plus the carbon dioxide plus the nitrogen, all the stuff that would have been in the smoke. And we add all of that up and we get 290.56. And then we divide it by the mass of the fuel, which we said was 16. And then we're multiplying it by the actual mass of fuel, which is 4 kilograms. And we end up with the mass of smoke that should be 72.64 kilograms. Okay? And then we said for the mass concentration, it's just the mass of carbon dioxide that we actually calculated. So that's our 10.88. And then we're dividing it by the mass of smoke that we just calculated. And so we do that calculation, and we end up with 0.498. And then the last step is to multiply that by the molar mass of air divided by the molar mass of the actual species. And so we get times 29 divided by 44 in this case. And we end up with 0.0987. Okay, so this now is in parts per million, 98, almost 99,000 parts per million. And if we want it as a percentage, we would just multiply it by 100 and get that 9.87. So we're just under 10% of the room is carbon dioxide after this fire has happened. Now, if we do the simpler method, we'll see all we have to do is do the mass of the species still, but divide it by the mass of all the air in the room. And when we do that, it's almost identical. Okay, so the mass of air is density of air, 1.21 kilograms per meter cubed, times the volume of the room. And we end up getting 0.1499 instead of 0.1498. Right? So it's almost identical. And if we round to 2 decimals, it's identical. And then we go through the same process and we end up with 98,800 parts per million instead of 98,700 parts per million. So almost, 98, 900, 700. Which one was it? 700, sorry. Yeah. So we're 100 extra doing the simplification. So we've actually been conservative by doing that. All right, so when we're looking at the mass and volume concentrations, that's the process that we get to. Now we know the percentage. Now we know the parts per million. We can use that value to determine the life safety of an occupant. So that's what we're going to get into next. But it's important to remember that the main factors for determining how dangerous the situation is going to be are the geometry of the enclosure. So what's burning? If we have the same fuel, then we don't have to worry about that, but the fuel type can change, right? So what is the fuel? Is it methane or is it a couch? Is it propane, gasoline? They're going to burn differently. They're going to create different amounts of products of combustion. And then how big is that enclosure where the products of combustion are collecting? And then what kind of ventilation is there in the enclosure? So how big is the doorway? Is there just one? Is there two? When can smoke start leaving? That will impact the concentrations. So all of that is super important. And where is that fuel? All right, so where does the fire start? And then where's the other fuel? So if we move things closer to the original fire, they'll catch on fire quicker. It'll create more products of combustion. All of that stuff has an impact. And so that's all important to remember. And so next we'll take a look at the calculations we can do to determine life safety. And that'll be the next video.